Hey, good morning, everybody. Um, I know that this is Wednesday, and Wednesday is a shortened day because we've got service projects this afternoon. Um, so I've limited the time here. Um, I did upload a video with me answering some homework questions from um, from the optimization. There's two questions, number 29 and number 44. So those are on YouTube. They're also on RenWeb. If you haven't already seen them, I think I might have already sent an email, but if I didn't, look at those. If looking through some of those solutions would be helpful to you. Um, today will be short. We're just going to go over the new section that we have on Newton's method. We'll talk about that. The quiz on Thursday, just FYI, the quiz is just on optimization. I'm not going to throw curve sketching and optimization. That's a lot of material on there. The optimization, I'm going to try, if I just put one problem on the quiz, if you don't get that problem, then you don't do well on the quiz. So I'm going to try to do two questions, but one of them is going to be a lot easier than the other one. I won't make the other one crazy, but will probably just be two optimization questions, okay? So I know have service day. My prayer for you guys as you're going out for service day, the passage that comes to my mind is Philippians chapter 2, where it says, don't just think of yourselves, but also think of others. Have this mind in you that's also in Christ Jesus, who was in very nature God, but he didn't think of that as something to be held onto, but he made himself nothing and took on the very form of a servant. And that's what you guys are doing today. So that's my prayer, that you would shine your light in the community so everybody else could see what you guys are doing and be drawn to the Lord. So we're going to go through one kind of short section. There's not a lot we're going to cover in this section. We could get more deep, but we don't have a lot of time today. This section is called Newton's method, and it's connected to a question that I asked earlier in the semester, and we're going to explore that question even more tomorrow, but we'll get a little bit into the idea of the question today. The question is related to how did your calculator actually calculate things? So if you think about taking the sine of 1.34, if you just put that in your calculator will spit something out. Question is, how is it calculating that number? Does it have all these different, an infinite number of things all memorized and it just spits them out when you ask it? The answer is no. It's actually doing a calculation, but in order to figure out what that calculation is, we need to have a few more tools. But related to that question is, if we wanted to calculate something that's kind of hard for us to calculate, like the square root of 2, and we didn't have a calculator, how would we get an approximation of it? How would we get close to it, or how would we know what it is? So if you were to put square root of 2 in your calculator, it would spit out 1.414213562 blah, blah, blah. Okay? So mathematicians, it turns out, calculating numbers is connected to solving equations. So solving the equation x squared minus 2 equals 0 is the same thing as finding the square root of 2. Okay, those are interconnected questions. And this idea of solving equations, when is a function equal to 0, or what values of x make a function equal to 0, is actually a question that a lot of mathematics kind of is connected to. When does a function equal 0? And if the same idea is, when do two functions equal? If we put one of the functions on the other side, then we're asking, when does this thing equal 0? So what was interesting is that once Newton developed some calculus methods, Newton figured out that there's a way to use calculus to give some partial answer to when do functions equal 0. And he figured out a way to get approximations, approximate answers to that question. So here's the idea behind what Newton found. So I'm just going to draw kind of an example function here. So this is where, if this is just some random function, this is where that function equals 0. If I don't know where that function equals 0, and I take a guess, let's say my guess is right here, I'm going to call that guess x1. Here's the brilliant idea that Newton had. Notice that in my setup here, if I were to guess here, and then at that place where I'm guessing, if I were to go up to the function and draw a tangent line and ask where does that tangent line hit the x-axis, that number is a better approximation to where the 0 is than the original thing that I did. And if I were to take that number and do the same thing again, go up to the function, draw a tangent line, wow, I get an even better approximation. And if I keep doing that, I keep getting a better and better and better approximation to where that 0 is on the function. Okay? So that's the idea behind what we're going to take a look at today. Now, what I want to do is derive a formula. Once you have x1, how do I get to x2? When I have x2, how do I get to x3? We want to get a formula for that. Once we have a formula for that, then we can just do it in several examples and see how this works. Okay? So let's draw a general formula here. Okay, so here's my 0 that I'm interested in, and I'm going to take some guess. Okay, here's x1, and then I've got my function, f of x1. And then I've got a tangent line that I'm creating right there, and that tangent line hits the x-axis somewhere. Okay, now to get the equation of a tangent line, because I want to figure out where does that tangent line hit the x-axis. In order to get the equation of a tangent line, I need a point that the tangent line is going through. So I've got a point x1, comma, f of x1. And I need a slope. Now the slope of the tangent line is the derivative there. So what I'm going to do is take my point slope form, y minus y1 equals slope times x minus x1. And I'm going to plug my information in here to get the equation of the tangent line. Minus my y value, f of x1, is the slope times x minus x1. So this is my equation of the tangent line right there at x1. Now what I'm curious about is where does that tangent line have a y value of 0? Where does it equal 0? So if y is 0, what is the x value? All of these other things are constants here. What's the x value here? That's what we're calling x2. So what we're going to do is we're going to solve this equation for x2, and we're going to see what ends up having to happen. So the 0 goes away. Let's divide by this slope. So f prime of x1 goes on the bottom. And then I'm going to move the x1 over. I'm going to add that over. And that gives me x2. So in other words, if I start with x1, then the way that I get my next number is I take x1 minus that number plugged into the function over that number plugged into the derivative. But this also tells me that if I want the next one, x3, I just take x2 and do that same thing and keep going kind of forever. So in other words, if I want a next step, I take the previous number that I'm at minus that number plugged into the function over that number plugged into the derivative, and that's going to give me my next step. This is Newton's method here. Okay. I hope I'm not going too fast for you guys here. This is actually the second time I recorded this lecture. I recorded the whole thing, and then my computer said, nope, I didn't take it. So it's the way it works sometimes. Yeah. So let's do a few examples of this using Newton's method. Okay. And using this formula that we have for getting better and better approximations. And the first example that we're going to do here is that example that I was mentioning before, x squared minus 2. Okay. All right. So what we're going to do, now you should know what this function actually looks like. X squared is like this. And then minus 2 means we go down 2. So 1, 2, up here, right? So what I'm going to do is I'm going to start with, I'm curious where this crosses. So I'm going to start with some guess. And in my case, I'm just going to randomly guess 1. This is going to be my x1 here. All right. And then I'm going to go up and take a tangent line to get my next value. And the question is, where is that? So I don't have to draw it to figure it out. I can just use my formula. So the next value is the first value minus f of the first value over f prime of the first value. Now that means I need the function and I need its derivative. So let's go ahead and calculate the derivative. The derivative is 2x. All right. So that means that I'm going to have to plug 1 into my function, and I'm going to have to plug 1 into the derivative. So if I plug 1 into the function, 1 minus 2 gives me negative 1. And if I plug 1 into the derivative, I get 2. So I get 1 plus a half, that's 1.5. So where that tangent line is going to land me is right between 1 and 2 at 1.5. Okay. Now my next approximation, I'm just going to take 1.5 minus f of 1.5 over f prime of 1.5. So I just stick 1.5, I stick the last one in everywhere. So in order to do this, I'm going to whip my calculator out, and I know that's cheating because we're pretending that we don't have calculators, but that's okay. So I'm going to take 1.5 squared minus 2, so I'm plugging that in the function and I get a quarter, 0.25. And then 1.5 plugged into the derivative gives me 3. Okay, so then I'm going to subtract, I'm going to divide those and subtract that from 5, and I get 1.416666. Okay. For our sake, we're going to take about 5 or 6 places, maybe take 6 places, so that we keep some accuracy. Let's go one more. So I'm going to take that number and then plug that into the function and plug it into the derivative. So if I plug that number in the function, I'm going to square it, minus 2, the original number, minus 0.00694, and then I'm going to take that same number, 1.416666, multiply by 2. All right, let's try that again. 1.4166. All right, and I get 2.83333. So let's divide 0.0069444 by that number, and then we're going to subtract that from 1.416666. And what we get here is 1.414215 7, ... Now what I want you to remember is that the square root of 2 is actually 1.41421335. Notice that we've already got a lot of accuracy just doing a couple of iterations here. We're on the 4th iteration, starting at 1, and we're already 5 or 6 decimal places in. So that's really, really, really good. Okay, you kind of get the idea for how this algorithm is finding the zeros of this function. So when does that function equal 0? Let's give it a try with one more example. Okay, I'm going to leave this formula up here. Okay, so let's try the example 2x cubed plus x minus 1. All right. So if you were to graph this, when x is 1, if you were to plug this in, 3 minus 1 is 2, so the function's up here. And when x is 0, it's negative 1. So this function actually does something kind of like this. So it has a 0 somewhere between 0 and 1. I'm curious where that is. Okay. So let's start with x equals 1 and just see what we end up getting here. So my next step, if I were to do that visually, coming up here, drawing a tangent line and getting something. So let's see what that something is. So I'm supposed to take 1 minus f of 1 over f prime of 1. Now, I need f prime, so let's do that. F prime is 6x squared plus 1, and then the derivative of minus 1 is 0. So 1 minus, if I plug 1 in here, we said before this is 2 plus 1 is 3 minus 1 is 2. If I plug 1 into the derivative, I get 7. So this is 5/7. In other words, let's get an approximation here. And again, I'm going to take about 6 digits. Okay. Now, a better approximation is by taking that number minus f of that number over f prime of that number. Okay. So what I'm going to do I'm going to plug that number into this function. So in other words, I'm going to cube it times 2 plus the original number, 0.714286 minus 1. Okay, and here I get 0.443149. And now if I were to take that same number, 0.714286, and square it times 6 plus 1, okay. And now if I compute this right here, so if I take these two numbers and divide them, and then subtract that from 714,286, I get 0.605169. Okay, and then an even better approximation is going to be, again, using that number minus f of that number over f prime of that number. Now, you might wonder, I don't know exactly what the solution is to this. How do I know when I'm close? Well, the way that you tell that you're close is you're only, wherever you're at, if this is my goal and this is like, let's say this is x5 and this is x6, whatever the difference is here, that's the worst that this difference can be to my goal. So in other words, since these two are off by about 0.1, this answer right here isn't any worse than 0.1 away from the actual answer. Okay? That kind of makes sense? So you'll have some homework problems where you're actually practicing using this. They give you a function and a starting point, and you practice using using this algorithm. Now, there's two things that I want to point out here. The first one is that this doesn't always work. While this is a really nice method, it does not always work. And kind of a simple example would be the cube root of x. Okay, there are actually several examples, and you're going to look at a couple of them on your homework. But one simple example would be the cube root of x. Okay, so x to the 1/3. So if I were, let's first draw it. Let me show you visually. Remember, there's a vertical tangent line at 0. If I didn't know where this 0 was, what I would do with Newton's method is I'd pick some number like 1, and I'd come in and draw a tangent line. Okay, and that would give me another point. Then I'd come down here, pick this point, and draw a tangent line. But now I think you probably see what's going on here. It just keeps getting worse and worse and worse. Okay? And that can happen. So if I were to actually use, let's use x1 is 1. In order to plug in, so x2 would be 1 minus f of 1 over f prime of 1. I need to figure out what f prime is here. So f prime is 1/3 x to the minus 2/3. That negative means it belongs on the bottom, so it's 1/3 cube root of x squared. So in this formula right here, I have 1 minus f of 1, the cube root of 1 is 1. And if you plug 1 into the derivative here, 1 squared is 1, cube root is 1. So I have 1/3 on the bottom here. But if you have 1/3 on the bottom, it flips up to become 3, and 1 minus 3 is -2. So if you start at 1, the next place you end up hitting is -2. And if you do this again, what you'll find is that the next value is actually 4. And then the next value is actually -8. And it just keeps getting worse and worse and worse. So it does not end up heading to 0. So Newton's method does not always guarantee an answer, which is an interesting thing. Now, how do you tell if it will give an answer? There's actually some criteria about the first derivative and the second derivative that's on page 225 if you're curious. You don't need to know those criteria, but there are some criteria there for that. One of the other interesting things that I just want to point out that's at the end of this section is that solving equations has actually been kind of in your blood for a little while, ever since you started with algebra. In particular, there's a formula that you memorized for how to solve ax squared plus bx plus c equals 0. And I know the second I start to write it down, it should come out of your mouth, -b plus or minus the square root of b squared minus 4ac all over 2a. That's our quadratic formula. Okay, that allows us to solve any quadratic where the term in front of the x squared is not 0. Okay, now here's an interesting historical fact is that there actually is a formula for how to solve a cubic. Okay, the formula here is actually called Cardano's formula. It's named after a named Cardano, who used to make money solving these types of equations. So this was back, in the 1700s. If you wanted to make money and you knew how to solve that kind of equation, you could have a competition and make some money. So believe it or not, it's true. The formula for solving this is actually 2 or 3 times as complicated as this. It's probably, if I were to write it out, it would be really long. Okay. Now later on, people ended up finding a formula for how to solve a 4th degree polynomial. This is called a quartic. Okay, and this formula is so complicated that it would fill most of this board. It's very, very, very complicated. But here's the very interesting thing. It turns out that once you get past 4th degree, 5th degree and higher, so 5th degree polynomial is called a quintic. A 5th degree polynomial and higher, there is no general formula for solving that type of, don't know it, it's that there is none. It's actually been proven that there is none. So there was a mathematician named Galois. He was a very interesting character. He ended up getting in a duel when he was around age 21 and got shot and died. So all of the work that Galois did was before age 21. But he ended up proving, using a very different method that takes a lot of background in order to understand. He ended up proving that for 5th degree and higher, there is no general formula. For in specific cases, there's a way to solve it. I mean, here's a silly example. X to the 5th minus 2 equals 0. You could figure that out. The answer is the 5th root of 2. Okay, that's not hard to do. But in general, is there a formula for 5th degree polynomials? The answer is no, which is shocking. It really shocked the mathematical community. Sort of showed the limits of human capacity. There are answers to what the solutions are, but there is no one formula that human can write down that can solve it. So it's pretty interesting mathematical fact there. All right, so if you have some extra time now, feel free to take that and use it to finish up either your curve sketching or optimization problems, and we will connect again on Thursday to talk about the last section in chapter 3, as well as to go through your quiz. All right, see you then.